Second. Okay, so Dr. Siamak Farajzadeh is a research fellow in computer-aided engineering. He has more than 10 years of industrial and academic experience in field of design, material characterization, and computational mechanics. He has got his PhD in aerospace engineering from University of Padova in Italy and worked as a research fellow at Imperial College London. He's currently working at UCL and EPICentre as well in an interdisciplinary project about the design and new generation of offshore helidecks for lighthouses. This is the topic that he's going to talk about today as well. As usual, the talks are short. After his talk is finished, we will have a Q&A session that you can either type it in the chat or feel free to unmute yourself and ask your question. Dr. Siamak, the floor is all yours if you want to share your screen.
Yes, hello everyone. Do you hear me?
Yes, perfect.
Okay, very good. Good afternoon everyone and welcome to this session. Okay, yes. Here we go. Do you see my screen now?
Yes.
Okay, very good. So good afternoon and welcome to this session. This is the first seminar from a series of seminars, I believe, from EPICentre this year. Okay, very good. So I just want to, if I can do that, I would like to turn off my camera to have a better connection. Okay, here we go. Okay, here it is. So my talk is about new generation of helidecks for lighthouses. And yeah, I try to be very brief and not very specific in details and try to keep everything in our time. So it goes through. Okay. So yeah, I'm working in the field of computer-aided engineering, CAE, and mainly in the field of computational mechanics. So you already know about my experience. And this project is mainly between Trinity House and University College London, UCL. Trinity House is the official authority taking care of lighthouses in the UK. And the PI of this project is Professor Dina Diayola at the Department of Civil, Environmental and Geomatic Engineering at UCL. And before going to details about the next generation of these structures, I would like to give you an overview about the current structures, current helidecks and lighthouses. So about the lighthouse itself. So probably most of you know what is a lighthouse, but you may not details about structures. So these structures have different parts depending their type actually, but the most important part is the lantern, which is shining, and it's the most important part considering the functionality of these structures. So here you see a drawing of the Eddystone lighthouse. So basically these lighthouses are like tall buildings, and you see they have different floors. So they have bedroom, they have kitchen, because people used to live there, especially for these remote lighthouses. And here you see also the lantern. The lantern is rather important for the design of helidecks as well, especially the glazing path lanterns. I tell you about them more a bit later. So this is the upper structure. This is the lower part of this structure. And we have, this is the actual Eddystone. So you just saw the drawing of this structure, this lighthouse. So we have 7 lighthouses in the UK equipped with helidecks on their top. We have more lighthouses, but these 7 are just those equipped with helidecks on their top. So this is Eddystone, and you see also the location of these lighthouses. Most of them in the south. This is it's very close to France, far from British coast. It's a long ship, very close to Cornwall, again in the south, small. So this is the only one between Wales and Ireland. This is Wolf Rock, again close to Cornwall. This is Bishop Rock that we have focused on. This one for the design. This is very to Isles of Scilly, and yeah, even though those pictures were really beautiful and you could see that the sea is very calm and nice, but these structures can be under really harsh environmental conditions and loading. And here you see the wave hitting Bishop Rock Lighthouse. So these structures are very robust. They have been there for more than 100 years, at least, under these conditions. Luckily for us, the wave doesn't go that much up, so it doesn't load that much the helideck on top of the structure. And this lighthouse is almost 45-46 meter. It's rather tall building in the middle of water. And looking at these helidecks on top of these lighthouses, we see, even though they are very similar, they have differences as well. As you may have recognized, they have different patterns considering these diagonal components which are supporting the structure and brace them. So the reason that they are different is because they are following the glazing pattern of the lantern. So here, this is the Bishop Rock helideck. On the right side, you see the glazing pattern. So this is on the lantern. On the left side, all the beams are the supporting beams for the helipad. Basically, they are part of the helideck structure. And to minimize the light obscuration of the lighthouse, the light, these structures, the helidecks, are exactly following the pattern, the same pattern of lantern glazing, because lantern glazing is obscuring the light. So we have some loss of light, I would say, because of these glazing. And we try to keep the light obscuration as minimum as possible by having the same pattern of a structure on the helideck, which is following the lantern glazing pattern. So here, this is very simple demonstration of this. So we have the light source, which is the light inside the lantern on top of the lighthouse. And then we have this one layer of obscuration and obstacles, which are lantern glazing. And then the second layer is the helideck. So if we have a different pattern, we will increase the light obscuration. But if we keep the pattern of the helideck as the lantern glazing, we would keep the light obscuration as minimum. So this is something important for us, but I'll talk about it later. But it has nothing to do with a structural integrity or a structural analysis of the structure. So our focus on this in this project is the Bishop Rock Lighthouse. Bishop Rock Lighthouse is very silly. You see it, and then if you stand on top of the helipad, you see nothing, just water, but you may see also Isles of Scilly in remote place. So yeah, this is our main concern for this project. But the method that we develop and we have developed for this structure can be used for other lighthouses as well. So this is the oldest drawing I could find from the Bishop Rock Lighthouse, and I believe this structure was just washed off by wave before starting its duty. And then they decided to make it a bit more robust. So they built a structure like this, and then they changed the design again, having a more serious structure and a stronger one. And this drawing is the drawing of the current Bishop Rock Lighthouse. It's a rather old drawing, but most of the drawings for these structures are rather old. And yeah, this is top of the lighthouse. And this picture is taken in 1966, before putting a helideck on top of this structure. And this structure was constructed in 1858 and started shining same year, 1st of September of that year. And I believe for that time, it's an impressive design. And yeah, it's very impressive to see these designs. So this is another interesting picture from the construction process of helideck on top of Bishop Rock Lighthouse back in 1976. And here is a close-up of the current structure. So you see the helideck has two main parts. So one is the supporting part, and the helipad, which is sitting on the supporting structure. And you see that the size of the helipad compared to the helicopter is rather small. So you don't have a very large area for landing. So the structure is made of carbon steel and made of rather, I would say, a lot of beams connected to each other using bolts and nuts. Some of them are welded, but most of them are connected using bolts and nuts via flange connections. Even though these designs are very impressive and the structure has been there and working for like 50, 60 years, I mean, the helideck, they have some problems. And the most important problem is the harsh environmental condition, which is inducing a lot of corrosion on the structure. And you see, despite all the coatings and all frequent inspections and maintenances, some parts are severely corroded. And fixing these things, these corrosions, it takes a lot of time and it's rather expensive. And every time that these people going there for inspection and maintenance, they have to burn a lot of carbon because they have to fly there. It's expensive and it's not really environmental friendly. So the authorities decided to invest in this research project to look at new generation of lighthouses to see if they can come up with a new design, which is more sustainable and needs less maintenance and inspection visits. So this is about this project. So we are looking at new materials. Basically, the initial idea was looking at aluminium and carbon fiber reinforced plastics. But composites would be very, very expensive for this size, for a structure in this size. So we focus on aluminium at the moment. So we are different researchers in different fields working together. You see the general workflow of this work. So I have colleagues in Holland, TU Delft, working on extreme environmental conditions analysis. And then another colleague in Plymouth University is working on computational fluid dynamic analysis. And from their analysis, I get the loading and then I generate a computational model of Helidecks. And using those computational models, we carry out optimization process and assessment of structures. And we are also in close collaboration with Trinity House and manufacturers and material suppliers to come up with the best design for these structures. So this is the sequence of the project. So the output of the analysis from our colleagues in Holland would go to analysis of computational fluid dynamics from Plymouth University, and then the output of that one would be used by myself as the input for my computational model. Then we go for further analysis later, like buckling analysis, things like that. I show you some of our works briefly. So the work has two main parts. One part, which is the I would say the biggest part, is computational work, and then we have some experimental work as well. So the computational work, to design a structure, the most important thing is the loading. So we know we should know the loading, then we can design a structure for that specific loading. So for loading, we follow the requirements of this standard, which is for offshore helicopter landing areas, CAP 437. And the requirements in this standard are these loading that you see here, different type of loading and different load cases as well. So we ignore the last one, the number 7, which is for floating platforms. So our platform is not floating. Here is a demonstration from my colleagues in TU Delft analysis. So they calculated the wind speed at the location of Bishop Rock. So this is the average load speed, which is 27 almost meter per second. And then the standard requires considering the fluctuation of the wind in a time period of 10 minutes. So here you see the fluctuation of the wind. And then another colleague in Plymouth University, he took the output of my colleagues in Holland as the input for his analysis. So basically here he defined the wind speed as the input for his CFD analysis. Here you see a section of the structure. The big light in the center is the lantern. It's the cross section of the lantern, and those small circles are vertical components of the helideck section of those components. And here you see how the air is going around this structure and how is the load because of this airflow. So here you see the load as a function of time in a time period of 10 minutes, and as the function of the location of these components of the helideck. So if you look at this demonstration at the right of this slide, you see X direction is the direction of the wind, and theta is the angle between the wind direction and the line which is connecting the center of this structure to that location of our interest. So then I use these loads with other loads to design and optimize the structure. So this is the type of structure, the type of the aircraft that we considered for this design. So bigger than this cannot be landed on this platform. So we assume this is 3,000 kg, a little bit more than the actual mass of the structure, mass of the aircraft. And we have to consider different load cases. So we had a meeting with pilots they said they tried their best to land at the center of the helipad, but this is not always the case because the weather condition might be different, so they may a little bit land off center, and loading the helideck off center would produce large moments at the base of this structure. So we considered edge landing as the worst loading case to design this structure. And here you see the demonstration of different loads for these structures. So we have also landing lateral load, which can be induced on the structure because of the again weather condition. They may slide and land at the same time, so the structure should also maintain its integrity on that kind of loading as well. And then after that, we start the topology optimization process. And very simple definition of topology optimization is reducing the volume fraction or the total mass of the structure while keeping its compliance minimum. So basically, we want to use exactly the amount of material which is needed for a specific application, because we believe more than that would be a waste of material. So you can carry out topology optimization in software packages, commercial software packages like Abacus, ANSYS, and usually you get really beautiful results. But this is not something that you can go to a manufacturer and ask them to build it. You may find such a manufacturer, but they would ask a lot of money for building such a structure. So by defining constraints on the structures, you can get really good ideas about the final design. But again, it's not still feasible to manufacture. So like this one, this is much better than the previous ones. And this one is also much better than the rest of them that I showed you, but still cannot make such structure easily, I would say. So what we decided, instead of using commercial software packages, to use an algorithm. So we have developed an algorithm just for beam structures, and we define these structures as you see here. So these are samples of these structures. On the left side, you see very stiff structure. On the right side, you see very compliant structure. But the optimal structure is something between them. So we have developed an algorithm to find that structure for us. So the algorithm works like this. It gets the input of the design. The input is like the diameter of the helideck, the height of that, number of sections and things like that. And then it generates a computational model of different configurations of those structures. And it runs all those simulations for all configurations in Abacus and generates a design space. Now, out of that design space, we can find the best design for our application. So this is just a simple demonstration of a helideck. So here is the side view. The helideck has 8 vertical sections and 1 layer of diagonal bracing. So here you see the code generates the finite element model of all these configurations that you just saw. And then here is the demonstration of the volume fraction of the whole design space. Actually, this is not the last version. We almost considered 200 cases. So here you see different numbers of circumferential sections at this bottom row is showing the plan view or top view of the structure. So you see that we have different numbers of circumferential sections, and at each of them, so this section, we have different numbers of diagonal bracing, and this horizontal line, this one, if you see my cursor, basically the first step in this curve is showing the result for different locations of just one layer of diagonal bracing. And here you see we show the compliance versus volume fraction for this design space, and we are interested in this region, highlighted region, which has the lowest volume fraction, and we carry for these structures in the design space. So here you see a stress distribution in one of these structures. So this one has just one layer of bracing right underneath the helideck, helipad. And you see the stresses are around 60 megapascals. It's not very high, but this is just for static analysis. Another important thing for us is post-buckling analysis and buckling analysis. We are highly concerned about the buckling capacity of these structures. I believe most of you know what is buckling, but for those who don't know, buckling is a failure mode which happens before reaching the yield of the material. So it's not just a function of the material properties, it's also a function of the geometry of the component. So for buckling analysis, I carried out RICS analysis in Abaqus. So RICS analysis gives us the equilibrium state of the structure. So it increases the load until the structure fails. So for this particular structure here, you see that the buckling is happening a little bit above the reference load. So the reference loads are those that you define for the software. So I've done this in Abaqus. So those loads that you define for Abaqus and are those that I showed you earlier, which are required by the standard. So this structure, this particular design is almost buckling when we increase the loads up to almost 10%. But we carried out RICS analysis for other type of analysis, for other type of structures. This one with 2 layers of diagonal bracing, and for different location of the second diagonal bracing, you see that the buckling capacity is changing a lot. So this one, when we put one layer of diagonal bracing at the bottom of the structure and another layer at the third place or third section out of 8 sections for this structure, you have the highest capacity, which is like almost 60% above the reference load. I've carried out the same analysis for the structure with just one layer of diagonal bracing, and here is the result, and here is the comparison of the result for the structure with 2 layers and 1 layer of diagonal bracing, and you see how the buckling capacity is changing. And here you see the stress distribution of these designs that I just showed you for 2 layers and 1 layer of one layer of diagonal bracing. So the level of the stresses are not very high, and they can maintain their integrity on the rather high loads, I would say, above the reference level. So by doing so and using aluminium instead of carbon steel, we could reduce the total mass of this structure by almost 60%. So this is the design. This comparison is done for the design out of the algorithm, but we have other limitations to consider, like manufacturing limitations and light obscuration concerns. And these concerns would change the design a bit. But we are developing this framework, which can be used for finding the best design. Then we can add also other layers of limitations and constraints. Another thing for us to be considered is the connections. So connections should be designed fully. So for design of the connections, we do something which is called submodeling technique in finite element method. So we carry out first the upper scale analysis, which means analysis of the whole structure, and then we find the weakest point of the structure. Then we isolate that area. We carry out another round of simulation at the lower scale with more details. So this is a connection of data structure, and we can simulate and model more details. Here you see the bolts, nuts, and connecting plates, and then we load this model with loads coming from the upper scale simulation, and then we can assess the design at different scales. So here you see the animation showing the load. So this one has two stages. The first stage is loading of the bolts, and then loading coming from the upper scale, which is the sliding of these different plates on top of each other. And we have done some experimental evaluations as well. Some of them is done, some others should be done. So one of them was model analysis of the structure. So we went with other colleagues. So this is Professor James Brown John from Exeter University. He put some accelerometers on different locations of the structure and excited the structure using the hammer, like the one that you see on the left side of this slide. And then he recorded the acceleration at different points of the structure. And using those accelerations, combining all these accelerations and doing some mathematical analysis, could estimate the natural frequencies of the structure. So here you see the result of his analysis. This is very good for us because this is a benchmark for us to validate our computational model. So I use these experimental data to validate my computational models. This is still in process, so I don't have the results of comparison between the experimental and numerical simulation here. And another thing was that assessment of the anchor bolts of the current structure, because the helideck is held down on top of the lighthouse using bolts which are inside the wall of the lighthouse. So this is a plan of the base of the helideck. So actually the helideck is anchored to this base structure, and this structure is bolted or anchored to the top of the lighthouse. So here you see it better. So we have different types of anchor bolts. Some are rather long, between 1.5 meters, the others up to 5 meters. These long anchor bolts are close to the inner wall of the lighthouse, and there are shorter ones which are almost 30 centimeters and are close to the outer surface of the lighthouse. So the idea is to use the same anchor bolts for the new generation of Helidecks. But we wanted to be sure that these anchor bolts are in a good condition. So we went there. We did some visual inspections, but for that part which is inside the wall, we had to use other methods. So this is another old drawing for a course of the lighthouse, because the lighthouse is made of different courses of stones on top of each other. So looking at those drawings and doing some calculations, we could measure the distance between the inner surface of the lighthouse wall and the bolt. And knowing these dimensions, I took this equipment called GPR, which is, I believe, geometric penetrating radar, ground penetrating radar, yes. And then using these two, we could scan the wall and see how are the bolts inside the wall. So this is different sections of one of the scans. So on the left side, you see it's 190 mm depth. This depth is the distance of that section from the inner surface of the lighthouse wall. And from 119 mm to 270 mm, you see different sections. And that vertical highlighted area, you see pixels with lower intensities. That's one of the bolts. And here you see also section by section of the scan. You may see other areas with lower densities, lower intensities, light intensities, I would say, which are the seams between the different sections of the stones. But the one on the left side, going from top of the scanned area to the down, is a section of one of the bolts. So to summarize, what we are doing is developing an algorithm which gets the lighthouse dimensions and like location and environmental conditions, does some calculations inside, so using MATLAB and Abacus, and then it gives us the best Helideck design out of design space. So it looks at different configurations of the design and then gives us the best possible design. Then, as I said, we have other concerns like manufacturing concerns that should be resolved with the manufacturer. So when we decide, or when the official authority decides about the manufacturer which is going to build this thing, they may have some other concerns. There are many concerns about these structures, about the manufacturing, shipping them to the place. but at the moment we have focused on the design itself. There are other things to be done. There are some other experiments should be done later about the connections, about the welded components to understand the actual limit of the structure. Yeah, this is what I wanted to tell you, and I would like also to say thanks to all of my colleagues, and yeah, many of them, especially Dina Diayala from our department, who is my manager and the PI of this project, and Peter Dobson from Trinity House, and other colleagues. And also thanks to EPSRC for funding this project. I would like to say thanks to Orange as well for organizing this seminar. If you have any question, either please ask now in chat or just like turn on your microphone, or you may drop me an email, and then we can further discuss any issue. And I would like to say thank to all of you for attending this session, and I would like to share this interesting code about lighthouses. So after working on this project, this code made me impressed a lot. So I hope you like it as well. So lighthouses don't go around to save people. They just stand there and shine. Thank you very much.
Thank you very much. Perfect as usual. Very interesting stuff specifically about the edge landing of the helipad, which I never thought about it, as well as that graph that you had from your colleagues, which were showing the forces on the sides of the lighthouse using the circle and the stresses over there. As usual, the floor is open for anyone who has any questions. Feel free to unmute yourself and ask the question, or type it in the chat. I will read it and Siamak will answer. But I have, as usual, several questions as well. You talked a little bit about the connections, so you haven't focused on them yet, but any suggestion for the material that you want to discuss with us?
Yes, we know the material, we know the grade of aluminum that we are going to use. We know the filler material for welded sections and also the bolts. This is actually the result of our meetings and discussions with manufacturer. I'm not sure if I'm allowed to share it with everyone here. So we know it, but I believe I cannot say it now.
No worries. So it will be aluminium, not any fiber carbon or any fancy bolts.
No, at the moment, yeah, our focus is on aluminium.
Okay. In one of your slides, you mentioned that the total mass has reduced significantly as expected. You're going from steel to aluminium. Yep. But what has happened to price in this optimization? Have you looked at the cost? Did the process considered anything about the cost at all?
Yeah, actually, the price of this structure made of aluminium is not very low, so it's not a cheap structure. But considering the reduction in the number of visit sessions and maintenance sessions, in total, like in few years, you see the reduction in price. So in the beginning, you don't see that reduction, but after a while you see that, because these structures made of aluminium, they require less inspections. So at the moment, they should do like frequent inspection to understand which part of the structure is corroded and which part needs maintenance. But aluminium is much better in harsh environmental conditions, especially in corrosive conditions like in the sea. So by passing the time, you see that these structures would be cheaper and they have a lower level of carbon footprint.
Yeah, for sure. Less health monitoring is required as well, and they're more robust. One thing about the helipad, I'm sure there is a massive impact when the helicopter lands. Are there any dampers or anything to reduce that, let's say,
No,
impact on the
that's a
structure?
good question. Actually, we had discussions about this with manufacturers, with Trinity House people, and also pilots. Then I flew there myself, and when the weather is nice, the landing is very smooth, so you don't see any impact. But to consider the effect of an emergency landing, we increase the load from the aircraft by a safety factor of 2.5, which is a rather high safety factor. So considering that safety factor, which is the requirement of CAP standard, we are sure that even if there is some sort of impact or emergency landing, the structure maintains its integrity. And by the way, when the weather is not very good, there is no pilot flying there.
Yeah, for sure. Okay. And someone is asking about the fact that when you're considering the weight of the helicopter, you are assuming probably the weight of equipment, personnel, the fuel,
Absolutely.
and everything. So it's the most maximum, and probably there are some factors as well added to that 2 times that you considered.
Absolutely. Actually, the type of the helicopter that we considered for design is McDonnell Douglas, but now helicopters flying there to these places are another type, and they are lighter than this type of helicopter, but we kept this to be safe, like in a safe side.
Okay, good. Again, if anyone has any questions, please feel free to write it either in the chat or unmute yourself and ask. Now, going back to, let's say, corrosion, probably you guys didn't like model any corrosion or anything. It wasn't necessary, but is there any way of modeling it in Abacus, for example? Do you reduce the strain as well as the elasticity? I don't know, like, do you have any ideas on how to model that?
I know there are people doing that, but not in Abacus. There is a method called peridynamics method. It's a meshless method. And there is a center in Strathclyde University, Center of Peridynamics Analysis, and I know they are doing that. So they model corrosion, basically, computationally, but it's not a finite element modeling technique. It's a meshless technique, and it's different. So it's a computational model, but it's not done in Abacus. But if there is anything in Abacus, I don't know.
Okay. Anyhow, hopefully after this structure, there won't be any corrosions around. Good to know that there is a method. Again, if anyone has any questions, I am running out of questions. But one thing that probably the last thing is regarding the installation. So currently there is a structure over there anchored to the structure. Yeah. One thing is, were these buildings, when they were designed, did all of them consider to have a helideck, even the old ones, or if it needed, the helideck is somewhere else? So you had to do an inspection of, okay, whether the structure is okay or not, or has there been any strengthening measures for the current structures?
You are talking about the lighthouse or the helideck?
I'm talking about the lighthouse, whether it can stand the weight of the helideck.
Yeah, actually, these helidecks are rather old, like more than 100, 200 years old. And at that time, there was no aim for building a helideck on top of them. But later in, I think 1950s, they started looking at this possibility because it was, I would say, it would take a lot of time to go there by boat. So they decided to put a helideck on top of these structures. So the lighthouse itself is like 200 years old, but the helideck is like 60, 50, 60 years old. And not all of these lighthouses, these British lighthouses, are equipped with helidecks. So there are just 7 of them at the moment. But I mean, on top of them, you may see some other lighthouses at the coast, which has a helideck next to them, but it's not on top of the lighthouse. But yeah, these helidecks are not very old. And I believe they did an impressive job with the design and installation of these helidecks, because they just took everything piece by piece, and then they erected the structure on top of the helideck. And the shipping is another issue now, because we would like to reduce the number of bolted connections and have welded connections, because we want to reduce the risk of sort of particular type of corrosion, which is called crevice corrosion. And it happens at the interfaces of the aluminium structures. So we would like to reduce the number of bolted connections, but it means that those pieces should be welded in a shop, and then they should take it to the shore and then ship it there, and then lift it by a helicopter. And all these things, I mean, these vehicles, either like road vehicles or ships or helicopters, they have their limited capacities. So we have to consider those limited capacities for the design of these welded sections as well.
Okay, perfect. Yeah, I was thinking of how to like do it, and all in my mind was that prefabrication. You take a boat all the way there, like what we do with oil platforms as well. It transfers them. Someone has to remove the helicopter has to remove the old one, take it all the way to the shore. Now come back and take the new one. Okay, and I think you have answered most of the questions in the chat as well with this last discussion. Yes, so that's it. Thank you very much.
Thank you.
I will share my screen for a second again.
Yeah, sure.
And yeah, so today we had the talk by Dr. Siamak Farajzadeh on next generation of helidecks for offshore lighthouses. And next week, we will have the talk by Professor Ian Robertson from Hawaii University on the status of tsunami design in the US. And then the week followed, we will have, on 14th of December, we will have climate change and mental health. And then we'll go on Christmas holidays. And when we come back, we will have future resilient urban communities in the era of artificial intelligence by Dr. Lee Soon. And we carry on with the coming talks all the way to March. So yes, if you follow us on the social media, you will see the events, and all of these recordings are available on our YouTube channel as well. So thank you very much again to our speaker, as well as all of the participants. See you later.
Thank you. Thank you very much. Have a good afternoon.
You too. Enjoy.
Bye, everyone.
Bye.